Hi, this is Dia, and this is our homework 2, the radiation across the electromagnetic spectrum.
My name is Kier Gurney, and the section that I focused on is line patterns on a TV screen, which is visible light and diffraction. When a light is shown on a TV screen, there are many small lines in a horizontal pattern that are visible, which are the pixels on the TV, and the light generated from the flashlight reflects a glare that extends outwards into multicolored rays, forming an even pattern. As you can see in these images, you can see the main white part of the glare, and then you can see the different colors as the rays extend outwards, with the red over here, the blues and the greens. This type of radiation is visible electromagnetic radiation. Visible electromagnetic radiation, which is the type of electromagnetic radiation that can be seen by the human eye, ranges from approximately 380 to 700 nanometers. This means that each photon has an energy ranging from 3.27 electron volts to 1.77 electron volts. This is a diagram of the LCD screen structure with the polarizing filter, which is this gray box at the front, being like the top layer of the screen, and the backlight being the very back of the screen. The backlight is the light source for the screen, and it's made up of fluorescent or LED lamps, depending on the TV. This light is diffused, and it's sent through many polarizing filters before it hits the liquid crystals. When there is an electric current, the orientation of these crystals change and manipulate the light that's emitted from the backlight. The angle that these crystals twist in is determined by the voltage that's applied. Next up is the RGB color filter, which is all of the pixels on the TV. Each pixel is made up of red, green, and blue subpixels, and each of them are controlled by thin film transistors that turn each one on or off, controlling how much light is passed through. Then is the glass substrate, which is the actual screen, and then is the final polarizing filter. This polarizing filter blocks light waves that are going in certain directions and reduces both glare and reflections. This image is a depiction of diffraction grating. Diffraction grating is where a light is shined at the screen and most of the light is directly reflected back, which is the main white glare that you see in these images. That this main white part. And the different colors that are visible on the rays are a result of some of this light being reflected back at an angle, with different colored wavelengths being deflected at different angles, which is these parts right here. The broadness of these rays are dependent on the color of wave, because, for example, red waves will be diffracted at a wider angle than other colors due to its longer wavelength. This phenomenon happens on TV screens because of the pixel structure, in which the pixel grid causes a diffraction to form rays in an X pattern. Which, right, if you look at this image, you can see these rays going outwards. In this diagram, it shows a white light being shined at this array of pixels, and while some of the light is reflected directly back, there are colors that show up in these rays, with like more reds being on the outer sides because they're they're reflected at a wider angle, while the blues are more inwards.
Today I'm going to talk about thermal imaging, which is a technology that measures temperature differences by detecting infrared radiation. Thermal imaging uses radiation in the 7 to 14 micrometer wavelength range, which we can't see with our own eyes. So we're working with invisible radiation, but it's all around us, being emitted constantly. Because infrared has lower energy compared to visible and ultraviolet light, it's much more associated with heat rather than light, which we can actually see. The physics behind it is that as temperature increases, atoms and molecules move faster. This increased motion causes objects to release more infrared radiation. So infrared radiation is essentially produced by the natural motion of particles in matter. Since we can't see infrared naturally, thermal cameras have to use artificial colors to show us what's happening. Blue represents the cooler areas and red represents the warmer areas. You can see this in the thermal image, how different parts of people's bodies show up in different colors based on their temperature. It makes the temperature differences immediately visible. First, the physical process. Thermal emission happens from all matter that has a temperature above absolute zero, so essentially everything around us. This is explained with the Stefan Boltzmann law and the Wien's displacement law. To put this in perspective, your body right now is emitting around 500 watts of thermal energy. Even something like a hot cup of coffee versus the room around it will show completely different levels of emission. The type of radiation we're dealing with is infrared electromagnetic radiation, which is what is outside and what we can see. When you look at the energy per quantum using the equation E equals hc over lambda, infrared photons carry about 0.09 to 0.18 volts of energy. To compare, UV light is 40 times more energetic, and visible light is 20 times more energetic than infrared. In terms of what happens to the human body, in terms of what the human body actually produces per second, we're talking about roughly 100 watts and a photon flux of about 10 to 21st photons per second. The detection method is when the thermal cameras use something called a microbolometer. The most important part is that it actually doesn't detect the photons directly. Instead, there's a process where the infrared photons hit the detector and heat up those tiny particles, which changes their resistance, and that resistance change gets converted into voltage. So it's responding to the temperature change, not the photons themselves. These instruments are incredibly sensitive. They can pick up temperature differences as small as 0.05 degrees Celsius.
Hello, my name is Hassan Abbas, and I'm going to be presenting my group's part of the AM radio. I'm going to be talking about what it is, the frequency, its energy per photon, and explain how it encodes its information. First of all, what is it? AM radio stands for amplitude modulation, and it sends out its sounds by changing the height of radio waves. Even though we can't see these waves, they're all around us. These waves carry information like music or voices from a broadcasting station to our radios. Instead of sending sounds directly, the AM radio sends a carrier wave that travels long distances. Then the sound gets added onto the wave by changing the amplitude or height. That's where the name amplitude modulation comes from. Now I would like to identify these properties of the AM radio. One important property of it is its frequency. AM radio compared to others frequencies has very low energy compared to one of, let's say, the FM radio. They carry about 500 to 1700 kilohertz. Because the frequency is a lot lower, they're usually considered much safer than, let's say, visible light. Another one of its properties is its energy per photon. Since AM radios don't carry much energy, they need to transmit or send a lot of photons together in order for it to get that signal across, since they do have to travel long distances. And another reason they can travel long distances is because their frequency level is so low, and this causes its wavelengths to be longer and travel those far distances. But they do have to send out a lot of energy per photons to get that signal across. AM radios encode information by changing the height of its sound waves. For example, for higher sounds, the radio will increase the height of the sound waves, and for quieter sounds, the AM will decrease the height of the sound waves. They also detect signals by using their antennas to catch sound waves. The radio removes the carrier wave and keeps only the changing part, I'm sorry. This changing signal is turned back into sounds by the speaker. And over here, I would like to show the sketch of an AM radio. Over here is the transmitter, and you can see the blue lines right here. Is it transmitting its signal over however far the distance is to the receiver? And the receiver up over here is catching it with its antenna. And this is the transmission, the transmitter over here, and then this will be the propagation. And yes, thank you for listening to this recording.
Hi, my name is Julianne, and I'll be talking about microwaves. So microwaves use electromagnetic radiation ranging from 300 megahertz to 300 gigahertz on the frequency scale. So this is a relatively high frequency as it is more on the upper spectrum of the scale. They emit long wavelengths, typically around 12.23 centimeters. To estimate the power, you would use the equation N equals P over HF. Small microwaves have around 600 to 800 watts. Standard microwaves have around 800 to 1000 watts. And then high-powered microwaves can reach up to more than 1000 watts. So overall, microwaves range from 600 to 1200 watts. When talking about the energy versus the total power of a microwave, the energy is indicated by the power of a single photon, while total power is indicated by the energy of many photons per second. So ultimately, total power would be a much bigger number. So going into the anatomy of a microwave, they have what is called a magnetron. And due to the magnetron, microwaves bounce off of the reflection of metal walls within the oven, resulting in waves. So the waves bouncing off the reflections kind of cause erratic behavior. So this is what causes the waves to kind of be like random within a microwave. It's pretty much what causes them to be continuously moving. The many waves produced interact with each other, resulting in areas of hot spots or areas of high energy, and areas of cold spots, areas of low energy, due to the opposite behavior of the waves. Electromagnetic waves are a form of radiation that have polar and nonpolar sections. The moving waves will rapidly spin polar molecules, like water, for example, resulting in thermal energy or heat due to this movement. So over here is a slide of the previous 4 photos, kind of more close up. In the top left, you can see a sketch of a microwave and the placement of the magnetron within it. In the top right corner, you can see a sketch of the magnetron itself and what is producing these waves. In the bottom left corner, you can see 2 waves interacting with each other, and you can see the antinodes, or the areas of a hotspot, and then you can see how it kind of comes in the middle here, where the waves will meet. You can see the nodes, which is an area of a cold spot. So this is sort of why sometimes food does not heat up evenly, and some bits are left cold. Over in the right bottom corner, you can see how polar molecules, in this case I included a sketch of water molecules interacting with a wave. So you can see how some parts of the waves are positively charged while others negatively charged, and the constant moving of the wave causes the molecule to once again spin rapidly as the wave is moving. And that's about it for microwaves.
And now the synthesis. Starting with energy per quantum versus biological impact. Ionization smoke detectors have high energy per particle and can ionize atoms, but short range limits biological exposure. UV lamp emits UV photons that can excite or damage biological molecules, so they both have usefulness and potential harm. TV line patterns using visible light have moderate energy and don't cause biological damage. Thermal imaging uses low energy infrared and primarily transfers heat rather than causing chemical or biological damage. Microwaves have very low energy and can cause heating when photons are absorbed. An AM radio has low energy and has no biological impact. For detectability by humans, ionization smoke detectors are invisible but detected directly through ionization of air. UV radiation is invisible to humans but can be detected through fluorescence. TV line patterns produce visible light that's detectable by human vision. Thermal imaging uses infrared, which is invisible and detected through thermal sensors. Microwaves are invisible and detected with antennas and electronic receivers. An AM radio is invisible and detected through radio receivers. Looking at the total power versus photon energy, ionization smoke detectors use low total power, but the alpha particles have high energy. UV lamps show that even low intensity can cause effects, but each photon carries high energy. TV line patterns use moderate total power with many moderate energy photons. Thermal imaging depends on detecting low energy infrared photons emitted by warmer objects, and microwaves work by using high total power rather than high energy photons. And AM radios rely on low energy photons over long distances. Finally, why some radiation ionizes and why others don't. Ionization smoke detectors ionize matter because each particle has enough energy to remove electrons from atoms. UV lamps can ionize or damage molecules due to the higher photon energy. Visible light from TV patterns doesn't ionize matter because photons lack the necessary energy. Thermal imaging doesn't ionize matter because infrared photons are too low in energy. Microwaves are too weak to ionize energy. In AM radio has the lowest photon energy and cannot cause ionization. So the key takeaway is that biological impact and ionization capability depend primarily on photon energy, while detection and heating effects can depend more on total power.